We are back to start a new chapter. In chapter 6, you recall we learned about what causes the wind to blow: high, low pressure, pressure gradient force, Coriolis effect, friction, centrifugal stuff, um, pressure patterns. We pretty much got that figured out, I think, and now we're going to see how it applies to actually explaining wind patterns all across the globe. We're going to start with a simple classification scheme of the scales of atmospheric motions. Well, guess what? There's micro scale, and that means little. And there's mesoscale, and that means medium. And there's macro scale, and that means big. Micro scale winds might be like a little swirl of leaves going across your front yard, temporary little gust of wind. We're talking about things, you know, less than 100 meters wide that last like less than a minute. But then there's mesoscale things, miles across, lasting many minutes, maybe an hour, things like a thunderstorm, where this side of town gets rained on and the wind blows a certain way. That's mesoscale. Also, perhaps a sea breeze that we're going to talk a lot more about later could be a mesoscale thing. And macro scale means big, like things that span hundreds of miles or more and last days, maybe even weeks. In fact, somebody decided later they had to divide that up more. So macro scale winds actually can range from synoptic level winds, which are like, you look at the weather map of the United States, and that's synoptic scale stuff, kind of things that you hear about for the next few days. And then there's enormous planetary scale things, giant eddies and waves in the jet stream and things like that. They're thousands of miles wide and last for weeks. So you'd have figured that. There's different scales of everything. There's different size rocks, There's different size wind patterns. But I'm going to start with what I will call some local winds. These are kind of colorful. I sort of like their names. It depends on what country they happen in. They got some neat name and story behind them or whatever. Give a few examples. Yeah. Well, first of all, here's one that you certainly have experienced unless you've literally never been to the beach. It's called the land sea breeze. Now, I could call it just a sea breeze, but it involves the land too. So maybe I'll say land sea breeze. And we really, I think we talked about this some before. If we didn't, we sure are going to now. I'm going to explain how it develops, and you will say, yes, I've lived it. Of course you have. Basically goes like this. Here's the land. Oops, I need some water. Yuck. I need some water too. It can't all be land or it won't be a land sea breeze. Here's the land, and here's the ocean, I guess. And there's going to be a palm tree. And we're going to have the sun come out. It's not that the sun shines just on the land, but I'll put the sun over the land. And at first, before you even get this thing going, just kind of as a default initial condition, let's imagine lines of equal pressure like that. That kind of spread out a little bit. And of course, I can probably, oh, squeaky, squeaky. I didn't know this would do that. Here's some isobars. They're not the kind of isobars that are looking down on the map. These are the kind where you're looking from the side and you're saying the pressure gets less as you go up. See, watch. So maybe this is 1,000 millibars, this is 900, and this is 800, and this is 700. Okay, when the sun comes out, let's say it heats the land, and it heats the land more than it heats the water, because the water doesn't heat very easily. We've got all kinds of reasons for that, like 4 of them that we learned we had on our test. But so the land is going to heat up more, and if it does, when it does, that's going to cause, the story, it's going to make the air over the land expand. So the air over the land gets all big and puffed up. See, watch it puff up. See how tall it's getting? Look at that air get tall. It got tall because the land got hot. In response to that, you see here at high levels, now this H doesn't mean up high. It's the relative pressure for that given height. In other words, look, this is like, whoa, 800 millibars, that's a lot of pressure for this many thousand feet up. Look over here, it's only 650. That's kind of low. You got a pressure gradient. You know what's going to happen. You're going to get the wind try to blow from high to low. I like that. The wind try to blow from high to low. You can remember that. So when the wind does blow from high to low, as we've talked about before, it's going to cause some redistribution of where this air is. Some of the air from over the land, where it's piled up all big and tall, is going to move out over the water, and that's going to make less air be over the land and more air be over the water. It won't completely erase the tendency for it to be tall over the land, but it will try. And as a result, well, oops, no, good grief. There. So at every level, initially in this picture, you have a flow out this way, trying to send air out over the water. So this person on the boat out here, see the happy little person? See, they're happy in the boat. They end up with air piling on top of them. If you get air piling on top of you, you're under pressure. And so relatively high pressure starts to form here. And as air leaves and ain't on top of you anymore, see this person here looking through a telescope at the person out at sea, this person gets less and less air under, the pressure gets kind of low. If this continues for a while, you'll end up with this situation. I'll kind of redraw it. You'll end up with a little bit higher up here, a little bit higher here, about level here, and eventually it'll go kind of like that. There's a nice picture in the book of this. You can look at that. But see, what's happened is you now have air flowing out to sea at high levels. But look, down at the surface where the pressure got kind of high here, it's pushing air back onto the land. So look at this, it's a sea breeze, and everybody goes down to the sea breeze and gets nice and cooled off, you know, because it's a hot day. So most of the times, I bet, when you've been to the beach, it's probably been in the summer, and you've mainly been out on the beach in the daytime. And this tends to peak, get most intense in the early afternoon when the land gets the most hotter than the water that it's ever going to get. So you get this circulation pattern. In fact, I bet, I never tried it, but I bet if you inflated a helium balloon just right, put just a little couple pennies on it or something so it's like neutral, you'd probably find that the balloon would tend to drift upwards here. Then you'd watch your little balloon go up to about like 4,000 feet up or something. I'm not quite sure how high the circulation might go. Might go up like 4,000 feet, go here, sink back down over the ocean, and maybe come back later. Maybe. So there's a general circulation like this, and it is strongest in the early afternoon when it's hot. But at night, cools down. The reason for this breeze to blow like this ceases to be. And then the land, generally, depends on what time of year, but generally speaking, the land is probably going to get cooler than the water because the water is so slow to cool off. As a result, you'll end up with the whole thing reversing, and you'll end up with what's called a land breeze, blowing out to sea and then flipping back around like this. You don't notice that a whole lot unless you go out to the beach first thing in the morning. You might notice the wind blowing out to sea. And it does depend on the time of year because the temperature difference and contrast is what matters. I might let you think about this question. What time of year do you think you'd get the strongest nighttime land breezes blowing out to water? What time of year? Let you think for a moment. Pause if you like. And now I'm going to answer your question. Be like in the late fall or maybe early winter, because that's when the water is still kind of warm, but the land is getting pretty cold. And it's that cold land that's going to get high pressure over it, you know, because the air all sinks down and more comes in and piles on top of it. We've talked about that before, and this is a specific application of it. So on a winter or late fall morning, you'd have this wind rushing out to sea. And on a late spring or early summer afternoon, it's coming in the strongest because then the water's still kind of cold and the land's pretty hot. So then you get the strongest sea breezes. So that's a sea breeze. As far as how big these things are, they're kind of mesoscale. It depends on how strong they get. The stronger they get, the bigger they get. And in my experience, I've gone to the beach sometimes, and in the summer, I start to have that salt smell. You know, you can smell the sea breeze and start feeling a little slight cooling of it when you're maybe a few miles from the beach. It fairly easily penetrates 5 miles inland, maybe 10, maybe even 20. And then there have been some cases, I know of in extreme places where there's cool water next to really hot land. Some sea breezes have penetrated more than 50 miles inland, or maybe just a few. And out to sea, you know, this breeze deal out here for like if you're sailing, you can probably depend on a land sea breeze cycle out to like 10, 20 miles offshore if you're sailing. How deep is it? A few thousand feet, something like that. So it's a land sea breeze, and you probably know about it. Okay, other breezes. And you know what? That same circulation pattern where you get a place that gets cold, gets high pressure at the surface, and wind blows from that to the hot place and back up and around, that is going to be a theme over and over again. Now, another wind is the mountain valley wind. I've experienced this a little bit. I don't live right next to the mountains, so I don't see it. Well, when I have been to the mountains, I felt it. Here's the deal. Here's a mountain. Here's a valley. Sun comes out. Sun beats down on the side of the mountain, makes the side of the mountain all hot because the sun's hitting it so directly, you know. And so when that gets hot, that hot air tends to rise. It's got to be replaced by something, so the air from the valley comes out like this. It probably flips over out here somewhere, but this is in the daytime. Daytime, when the sun's out. Oh, I'll do nighttime now. At night, when the moon's out, sometimes the moon looks like that. That's where we live. When the moon's out, the side of the mountain radiates infrared into space, and this gets cold, and this cold air comes flying down the side of the mountain. So the general tendency, if you live near mountains, is not always, but there tends to be a wind blowing from the mountains at night as cold air slides down the mountain and out into the valley. And in the daytime, very often the wind is blowing towards the mountain so it can rise up the side and do that business. Mountain valley breeze. And most of those don't have fancy names, but one of those is coming up pretty soon. Okay, here's another kind of wind. Another wind that has to do with mountains. It's when you have a mountain and then there's a valley over here. And the wind blows over the mountain and comes down the other side. Oh, that is familiar. That's like Misty Mountain. I didn't bother to name the wind that would blow in this case, but I am now. Let me tell you some places this happens. One place is the Rocky Mountains. If you're in Colorado all the way up to Alberta, Canada, you're going to get the situation where wind it's basically from the Pacific Ocean originally, going to climb over the mountains and come back down. So what's it going to be like? It's going to be like Cactus County. You know what's going to happen? You're going to get rain and snow or whatever on this side of the mountain. There's going to get all dried out. Then it's going to come down and take Dollar Drive the whole way down to get all hot and dry, really low relative humidity. So this wind that blows down into Cactus County is hot and dry, or at least warmer and drier than it would be otherwise. Out in Colorado, Wyoming, Montana, Alberta, Canada, all out in there, it's called a Chinook. Chinook is a Native American word. Apparently means snow eater because it eats up the snow. You know, it's like been snowing all over here, you know. And then this warm, dry wind comes in and eats up the snow. It's kind of famous because temperatures sometimes rise, like 40 degrees in a few minutes. I have a friend who lives in Lethbridge, Alberta, and he has experienced some serious Chinooks there. I visited, it wasn't a Chinook the day I was there, but by the way, these names get used for other things. There is something called a Chinook. Can you guess what it is? It's a military helicopter. It's called a Chinook. I forget the letters that go with it, the letters and numbers. But a Chinook is a great big military helicopter. Get it? Wind helicopter. There's other places this happens. This also can happen if this is like Italy and this is like Munich, Germany, and it blows. They don't call it a Chinook. And this is the Alps now. It's not called a Chinook anymore. It's got a German word. Um, I'll go ahead and say it. If I had German exchange students here, which I have had in meteorology before, they would tell me right away. They say, das Föhn, das Föhn. It's either spelled that way, or if you know any German, you can also put an umlaut over the O and mean the same thing. They're equal. Anyway, the Föhn, I hope I'm saying that about right, is a warm, dry wind blows down, and it's like it's Oktoberfest here, and those they're walking around with big old beer things or something, and whoosh, big old warm, dry wind blows them over. I'm not sure that usually happens, but it's a warm, dry wind in southern Germany called the Föhn. And, you know, there's a helicopter named after a Chinook. Is anything named after a Föhn? Yes, there is a brand of certain personal appliance sold in Germany. I've seen one because my wife's sister-in-law is German. So I've seen one of these. Guess what kind of thing it is? It is a hair dryer, blow dryer. See, it blows hot, dry air like Föhn. That's Föhn. So anyway, we got Föhn or Chinook type winds that blow in various parts of the world. That's one worth knowing. And the next one after the Föhn, oh yeah, I can't leave this out. I love the name of the wind in general. It's called a katabatic wind. Katabatic wind. A katabatic wind works like this. Kata means cold, basically. This is a wind because of coldness. What cold thing is it? What's this? Generally speaking, you have a plateau, and then a big drop off, and a low place down here. Maybe the sea, maybe down here, just a valley or something. But you have a big flat place. And in the winter, it may snow a bunch. Look at all that snow covering up that place. And snow is all bright and shiny and reflects the sunlight away. It's also a very good infrared radiator. So that white snow cover is great at getting rid of heat. And it gets really cold. Really, really cold up there. That really, really cold air forms this dome of cold air. It's very dense and it's heavy. And once it finds out about this cliff, it goes, look guys, and there it goes. It's like a giant waterfall, but it's not water, it's air. And this big slab of cold air comes rushing down the side of the mountain fast because it's heavy and really flows. Now, it certainly warms up on the way down. It has to. It takes Dollar Drive the whole way down. It warms up. But it's so cold in the first place that these people still think it's pretty cold. It comes blasting out across whatever this is. A lot of times it's a beach. I'll tell you a couple places in the world this happens. It happens in Serbia, not Serbia, the former Yugoslavia area along the Adriatic. There it's called the Bora, but the one I'll tell you happens on like the French Riviera, like around Monaco, Monte Carlo. And I have a weather program customer, I think I might have told you, who I found out lives right at the top of that hill where they film all the James Bond chase scenes on the side of the thing down in Monte Carlo. It's kind of famous. Anyway, he lives right up on top of this thing. And it's a guy named Guy, or Guy. Anyway, heard from him the other day. In any case, this wind blasts down into this area, and I have a mental image. I've never been there. I've never been to Europe. I'll go one day. I imagine people not sufficiently dressed on the beach. I'm imagining, people that probably don't need to be wearing teeny little things out on the beach and being unsightly or something. This wind takes care of it, because what happens is wind comes blasting down and causes thong-clad elderfolken to rush back into their casinos because it's cold. Anyway, it's called Le Mistral. Probably didn't do my French quite right there. So the Mistral is this cold katabatic wind. Another place you get them is Antarctica, but you don't go there very often. So anyway, we got katabatic winds. What else is there? I like this next one. This one called the country breeze. Country breeze. Sounds like it could be a brand of air freshener. Maybe orange juice. I don't know. It just sounds good, whatever it is. So what's the country breeze? Well, you don't have a country unless you got the city to go with it. So here's the way this works. You got the city. There's the city. You can tell because it's got the buildings. There's the city. Here's the country. So at night, the country gets nice and cool because it's radiating all this heat out. And the city with all that concrete and all that stuff going on is hotter. So it's relatively hot here and relatively cool out here and cool out here. And so what that does, it causes the air to bubble up all big over here and spill out this way and then create high pressure here and high pressure here and low pressure here. And the wind blows from the country into the city and then up and then back out again like that. That's at night mainly. I'm not sure it reverses all of the daytime, but that's called the country breeze. And now you know a lot of the local winds. It's time to scale it up. All these things were, I'd say, mesoscale. All those things are mesoscale. It's time to scale it up. We're going to now talk about something really important. I love anything global, like, about the whole world and how the whole world works. That's what we're getting at now. So, global circulation. This is actually for reference. Looks like I'm flipping on through here. I'm already in section 7.3. All right, so here's the Earth. And it has an equator. Here's the equator. Got the North Pole and the South Pole, and the sun shines on it. And since the sun shines on the equator, more of the equator gets hotter. You knew that. So if I started out with the atmosphere being, let's say, this deep. Now, the atmosphere does not have a lid on it. It's not an exact, it's a blurry deep. It fades out with altitude. But anyway, here's the atmosphere initially. Until I start applying the heat. When I turn the heat on, who gets the most heat? The equator gets the most heat, of course. So the equator gets hot, and the poles are cold. And what's the result of it being hot at the equator and cold at the poles? I'll maybe draw it red or something. Here we go. So it's going to go kind of like this. The air is going to shrink down over the poles and puff up over the equator and shrink down over the poles and puff up over the equator, shrink down over the poles. It's going to make the air taller over the equator than it is over the poles. And you know what that does? It's one big sea breeze. You got the sea breeze thing down now, don't you? With the air all tall up here, air is going to flow away from the equator at high altitudes. That is going to cause the surface pressure at the equator to get pretty low because the air is leaving, going away, it ain't on top of you anymore. That very same air is going to pile up over the poles and cause the pressure at the poles to get kind of high. Theoretically, and what's going to happen here, I'll give you a little bit of warning, this is going to be about a 3-stage iterative, like we're going to fix it repeatedly. The first thing I'm going to show you is not really quite what happens, and neither is the second thing I'm going to show you. By the time we get to the third thing, or maybe the fourth, it's going to be just about right. But anyway, the first thing I would think would happen is these winds would flow from the equator towards the poles at high altitudes, like it does with the sea breeze. And then at low levels, close to the surface, the high pressure at the poles would cause the wind to head back towards the equator. And I can draw this kind of, I've drawn around the edges here. Let me draw this all over the place. You would expect then, at the surface, near the ground, winds to flow from the poles towards the equator. You would also expect, way up high, many thousands of feet up, upper air, you would expect the wind to return back to the poles and it'd be like 2 giant circulation cells, one in each hemisphere. If this were true, and it partly is, if it were true, then people in the northern hemisphere on the ground would always feel the wind blowing from the North Pole towards the equator to go to the equator and then rise. And the high clouds, like up at 30,000 feet, would always be heading towards the poles to complete the trip and make the circulation pattern. Again, the circulation is going to look like that. And it's like these interlocking gear things, you know. Your book has pictures too. But that's what you would expect. The big thing here is called a Hadley cell. It's theoretically kind of what ought to happen. But it didn't quite work out that way because we got to put a twist on things because, you know, the Earth ain't just sitting there. It's spinning. And you know what happens when the Earth spins? You get a Coriolis effect. So what I'm going to try to do, again, I'm going to successively fix this picture. I'll leave this one up for the moment and draw another one down below it. So here we go. Here is the round Earth, and it should have this going on. But if the Coriolis effect kicks in, that deflects any wind in the northern hemisphere towards its right as it travels, and winds in the southern hemisphere towards its left. So let me tentatively, temporarily draw what that ought to do. So that ought to do something like this. It ought to make the wind go like, yep, it ought to do that. It ought to do that. And that's in the lower atmosphere. And up high, I'm using the same scheme up here. The green's down low and the red's up high. You ought to have the wind get bent this way, like that. Okay? So this would predict, and there's friction. There's some friction, so it doesn't quite go geostrophic. But at least maybe the upper level would. But, so what's going to happen is the wind should be from the northeast all over the northern hemisphere and should be from the southeast all over the southern hemisphere. It's not quite true. It is true anywhere between about here and here. There's a pretty good strip of the Earth called the tropics where that is true. But there's a problem. Now, I'm about to explain this in a way that's a cheap shortcut, but a very powerful one. I'm going to use what's called a teleological explanation. Do you remember when I said the wind blows in order to enforce, of all things, thermal socialism? You know, like redistributing the thermal wealth all over the world, and the wind like goes like, it's like Robin Hood, you know. The wind like steals from the rich equator and takes it to the cold poles and brings it back and so forth. So we talked about that. In the same sense, there's a purpose of fixing something here. There's a problem with this picture. If the wind is really blowing this way all the time, the wind at the surface where it rubs against the ground is really blowing towards the westish kind of all the time, it would do something really naughty. It would stop the Earth from rotating. That can't happen. We can't have that. A spinning thing can't stop itself from spinning. Something external would have to do it, and that's part of the system. We can't have this. We can't have the wind do this. So to fix this, here is the solution the Earth comes up with. I'm acting like the Earth is being clever here, coming up with a neat solution. Actually, it's one of those things where you put it on a supercomputer, you model every little chunk of air, and you make it obey all the laws of physics. It just happens. But to we people who can't like fathom all the little vectors and all the gazillion little things interacting, it ends up looking like it's got a mind of its own. And here's what it does. It ends up doing this. You do get the theoretical wind here near the equator, and you do get it again near the poles, but you can't have it everywhere because it'll stop the Earth from spinning. So in the mid-latitudes, it turns around and goes the other way. Now that's not, I'm going to admit, that's not especially obvious that would happen, but it does happen. And what we can do is we can now divide the Earth into these strips, and there are 3 zones in each hemisphere. There's a zone near the poles where the wind does the from the east kind of thing like you'd think it would. There's also a zone near the equator where it also does that. But there's an exception in the mid latitudes where we live, where the wind mostly blows from the west. I could probably explain it a little bit better than that. It has to do with the Coriolis effect and the air piling up, and I could work our way through an explanation, but I'm going to let it be with this for now. Give these things their names. Yes, these little zones have names. First of all, the least interest, pressure goes with it. Yes, indeed. We have high pressure at the poles. We do indeed. We also have low pressure at the equator, just like we thought. But you end up with a zone of low pressure called the subpolar low, and a zone of high pressure where air kind of piles up called the subtropical high. Now, those are technical sounding but very descriptive names. They make sense. But they have such neat names. Oh, gosh. This area here is called the trade winds. Sounds like the name of a motel in Florida. I'm sure there are lots of motels, the ones across the street from the nice ones at the beach, with the palm tree, a little flickering sign. The trade winds. The trade winds are these winds that they used for trade, because when they come over from Europe, in a little sailing boat, they could catch hold of the trade winds and go all the way to the Caribbean or Florida or something, riding the trade winds the whole way. And they're so dependable that they do make the palm trees bend. You look at those tropical islands, palm trees bend over a lot, So that's the trade winds, and they're in both hemispheres, northeasterly winds in the northern, southeasterly in the southern. The actual low pressure system itself here has almost no wind at all, because the air is coming from both directions and goes up. The fancy name for it is the intertropical convergence zone. It's in your book, intertropical convergence zone. But it's also colorfully called the doldrums. Now, the doldrums is the name of it, but the doldrums is also, I don't know if you ever used the word this way, it also means you're depressed. People in the doldrums just can't get out of the dumps. They're like in the gutter, the dumps, a rut, life's just, can't go anywhere. You know why? Because sailing ships that would get in the doldrums of the ITCZ couldn't go much of anywhere because the wind kind of quit blowing. They blow a little bit and they'd eventually get out, but they get stuck here. It's all hot and humid. Now, this place, the subpolar high, has another name. It's called the horse latitudes. Is that because many horses are found there? Swimming around in the water. Seahorses? No. This is where people would also get stuck because they'd be under high pressure with the wind blowing that way and that way, and they couldn't go anywhere. And they get stuck. And they have horses on board because they're conquistadors or something, And they have horses on board, and they can't feed the horses, so they throw the horses out and let the horses swim for themselves. Maybe even eat one of the horses because they couldn't take care of them. It's called the horse latitudes because people threw the horses in there. It's also where, guess what's there? I'll show you a place in the horse latitudes. Bermuda Triangle. I don't think the Bermuda Triangle is that scary, but it is in the horse latitudes. It's scary for horses. And this is the westerlies, the mid-latitude westerlies. I can see my time is running. I'm almost 30-some minutes now. And this, the subpolar low, is a stormy place like Iceland and subpolar low. It's like Iceland and the Aleutians, and it storms a lot. It's cloudy and all that. And here is the polar high where it's cold and clear. There's more I got to talk about with this, but please look in your book about the 3-cell circulation pattern. And you know what? It turns out it's not even quite completely right either, but we'll get to that later. We're at 34 minutes. Talk to you later. Bye.